Okay, hello everybody. We start our lecture 24, and according to counting of working days and holidays in Russia, it seems that we have only a possibility of 28 lectures without extra days. I asked organizers, and since 30 lectures were planned, I'll give you extra 2 lectures on Saturdays, which are working in next weeks. We have 2 working Saturdays, namely this week, 26th of December, and the last week of classes. It will be 16th of January. So I'll give you 2 extra lectures. Опять я не вижу чата. Okay, I hope it's clear now. So, today's section is L'Hopital rule. Case infinity over infinity. And we formulate slightly different version of the theorem, a little bit more general, and it is like that. So let fg be differentiable on AB without x tilde. X tilde belongs to the interval limit as x tends to x tilde f of x equals to the limit as x tends to x tilde g of x equals to infinity. Okay, maybe it is better plus or minus infinity to indicate. It might be minus infinity as well. And also we suppose that g prime of x is not equal to 0 for x in a neighborhood of punctured neighborhood of let's say delta x tilde without x tilde itself, punctured neighborhood. So there exists delta greater than 0 such that with delta greater than 0. If there exists the limit as x tends to x tilde of f prime of x over g prime of x equals to L, then there exists limit as x tends to x tilde f of x over g of x, and it is equal to the same value L. So the conditions are quite similar to the conditions of the case 0 over 0, except for we don't suppose differentiability at x tilde need not to be satisfied. Okay, proof. In fact, in your lecture notes, only the case of finite L is considered, and I'll give the proof for more general assertion, which includes also infinite values. So here we don't suppose that L is a finite number. So L might be an infinity. Plus or minus, doesn't matter. So firstly, we'll proceed like in lecture notes. So firstly, consider the case L is finite. And how we'll proceed in this case? So, in fact, we need to consider the ratio f of x over g of x, and to consider the difference between this ratio and L. And we want to prove that this difference will be as small as we want once we suppose x is sufficiently close to x tilde. Now we cannot proceed like in the case 0 over 0, because in fact we don't know, in fact we know that the limit at x tilde is infinite of both f and g, so it makes no sense to try to write down f of x minus f of x tilde, let's say. So, how we'll proceed in this case? Roughly speaking, the general idea is as follows. So, we create a difference like that. And look, we need to cancel this difference, right? So g of x minus g of alpha. And we need to cancel this difference, so it means we need to divide by that. So f of x over f of x minus f of alpha, right? And no, that is not precise, sorry. So look, this difference with a fixed alpha we can proceed somehow, but the idea is the following. So roughly speaking, look, maybe I'll consider a different line. So f of x, right? We'll present it as f of x times 1 minus f of alpha over f of x. So what is it? That is f of x minus f of alpha, right? Yeah, that is different, a little bit different. F of x minus f of alpha we may represent like that, right? Yeah. And then, analogously, we may represent g of x minus g of alpha. I don't explain yet what is it alpha here. We'll see it a little bit later. So now we have those identities, and then we see that the ratio f of x over g of x can be represented then as follows. So that is f of x minus f of alpha over g of x minus g of alpha. And then, yeah, I should divide it by 1 minus f of alpha over f of x over 1 minus g of alpha over g of x. So that is a general idea how to represent our ratio. So we want to study this ratio, f of x over g of x. What is it? We want to represent this ratio, right? And we represent it to be able to use again, like in the case 0 over 0, the Coshi mean value theorem. So we want to get some fixed alpha, and then if alpha is fixed, x tends to x tilde, we know f of x tends to infinity, g of x tends to infinity, so this ratio tends to 1. So let us denote this ratio as h alpha of x, that is 1 minus f of alpha over f of x over 1 minus g of alpha over g of x. So for arbitrary fixed alpha, once we fix alpha, limit as x tends to x tilde, h alpha of x equals to 1. So now we proceed along the following lines. Look, so okay, what is better then? So we have to consider the difference. Yeah. Yeah, I'll write like that, 1 over h alpha of x, that difference which we want to study. Yeah. Okay, so now let us use the information which we know from the conditions of the theorem. Look, we know the limit of f prime over g prime equals to L. Let me use this information. So L is finite, and the limit, hence the limit of our ratio is finite. Hence, there exists k positive, there exists delta. Okay, I may use just that one, doesn't matter. Okay, let it be smaller maybe, right? Let it be delta 1, there exists delta 1, and let it be positive and delta 1 less than delta, which is here. We may suppose it without loss of generality, such that this ratio f prime of x over g prime of x is bounded for all x from okay, I'll consider only the right neighborhood, x tilde plus delta 1. So once we have finite limit of some expression, we can be sure this expression is bounded in the neighborhood of x tilde. And in fact, I want to prove that from the right-hand side limit follows the right-hand side limit for the ratio of the functions. So it's slightly different assertion, of course, right? But once we will prove that, so if limit from the right is checked, analogously we can check the limit from the left-hand side, and altogether they give the limit. So we'll check this assertion, and we use the boundedness of the ratio, and also we'll use that for arbitrary epsilon greater than 0, there exists, let it be delta 2 greater than 0, such that for all x from x tilde plus delta 2, we have f prime of x over g prime of x minus L is less than epsilon. Epsilon maybe over 2. Okay. Epsilon over 2, let's say. Okay. Now, we know g prime of x is not 0 for x which belong to delta neighborhood. Hence, we can fix alpha which belongs to this neighborhood, where in fact, since I am considering only right-hand side, so let it be x tilde plus delta. So we fix arbitrary alpha from right neighborhood of x tilde. Then we can, for arbitrary x from this interval x tilde alpha, we can consider the segment x alpha, and then both functions f and g satisfy all conditions of the Coshi mean value theorem. Coshi mean value theorem. Because both are continuous here, x is in the interval where both functions are differentiable, and both are differentiable here, and moreover the derivative is not zero, but we'll write Coshi theorem like that. So hence we have f of alpha minus f of x times g prime at c equals to g of alpha minus g of x times f prime of c for c which is somewhere in the interval x alpha. That is Coshi mean value theorem. And since g prime is never zero, the difference g of alpha minus g of x cannot be zero, otherwise, according to Rolle theorem, derivative of g should be zero somewhere between, but it is never zero according to our supposition. So we can divide by everything what related to g, and it gives the ratio g of x minus g of alpha equals to f prime of c over g prime of c. Now, okay, how it's better to proceed? Let me. I have used this. This is not important anymore. Okay. Okay. Yeah, I forget to insert here minus L. So how? Okay, let me continue this line. So forget about that. H alpha I still need. So we need to consider this difference. We represent it like that, right? Where H alpha is defined by this equality, and then I can write this as g prime of c times 1 over h alpha of x minus L according to the Coshi mean value theorem. Then we represent it as f prime of c over g prime of c times 1 over h alpha of x minus 1 plus f prime of c over g prime of c minus L. So we add and subtract same expression f prime of c over g prime of c, right? Okay, now we are able to finish the proof. How? Look, first of all, I'll use boundedness of the ratio f prime over g prime. And then, because of the limit, so we know the limit h alpha of x equals to 1, hence we know that there exists, let's say, delta, which number? Delta 3 greater than 0, such that for all x, okay, I'll consider only right neighborhood, x tilde plus delta 3, for all x from that interval, we have 1 over h alpha of x minus 1 is less than epsilon over 2k. That is the estimate which is necessary. So, once again, alpha is fixed, f of x by the condition of our theorem tends to infinity, hence this ratio tends to 0. Same is true for that ratio, so we have this function tends to 1. And once it tends to 1, 1 over h alpha also tends to 1, and we have the following estimate. Moreover, now I'll use the second part. So once again, we used the equality for the limit of ratio of derivatives in two possible forms. One gives us boundedness, I used it here. Another is just the definition. So, if alpha, okay, so I need to fix alpha from, yeah, it should be, yeah. So here I fixed alpha from x tilde plus delta. No, I should be more careful. I want to use this inequality, hence I need to substitute here not delta, but let's say minimum of delta and delta 2. Yeah. So we fix alpha from that interval. If alpha is fixed from that interval, then the value of c, which we found by Coshi mean value theorem, will be also inside that interval, and it means that c satisfies the inequality f prime of c over g prime of c minus L is smaller than epsilon over 2. Now we unify those two inequalities, and we obtain, so let me put modulus here everywhere, and we have less or equal modulo f prime of c over g prime of c times modulo 1 over h alpha of x minus 1 plus modulo f prime of c over g prime of c minus l less than, so f prime over g prime is less or equal than k, modulus of the difference less than epsilon over 2k, and the last difference is smaller than epsilon over 2. So altogether it gives epsilon. So we have found some number, which number in fact minimum of delta 3 and this minimum. So once x belongs to the interval from x tilde to that x tilde plus that minimum, all inequalities are satisfied, which were used during the proof, and the chain of inequalities gives modulo of difference less than epsilon. And that is precisely h alpha of x. h alpha of x is that one. That is the function. That is the definition, h alpha of x. What means you don't understand what is h alpha of x? That is the definition. h alpha of x is a function which is defined by this equality. So alpha is fixed, or we fix alpha somewhere from that interval. So once again, let me give an overview. So take arbitrary epsilon greater than 0. Then there exists delta 2 greater than 0 such that this inequality holds. So now we fix alpha, arbitrary number from that interval. Right? We fix alpha. We consider the function h alpha of x, which is defined by that equality. Then, for all x from the interval from x tilde up to alpha, we can apply Coshi mean value theorem for the interval x alpha, which gives us that equality. And since c is somewhere between x and alpha, c will be also somewhere in that interval from x tilde up to x tilde plus delta 2 because of that. And it means that for f prime of c over g prime of c, we have same inequality as it was written here. Then we represent our difference f of x over g of x minus l by that chain of equalities and proceed. So the last step, you see here less than epsilon over 2. The last step is to estimate the first inequality using the fact that limit as x tends to x tilde h alpha of x equals to 1. Is it okay? Did I answer the question, what is h alpha of x, or not? Okay, I think I answered. So, once again, I would like to remark that in fact we have proved slightly different assertion, which is formally more general. We didn't consider just from the existence of this limit follows the existence of that limit. We have proved even more general thing, that from the existence of one-sided limit follows the existence of one-sided limit. And if we have from the beginning we have the existence of the limit, then both one-sided limit, right hand side and left hand side limits exist, and we use that right hand side and left hand side limits of the ratio f of x over g of x also exist. Okay, it was about the case of finite L. So what to do for infinite? So okay, I should modify. Let me modify now. So secondly, let L be equal to, let's say, plus infinity, right? Minus infinity is quite analogous. So L is infinity. Then what we have to prove? Let me write down what we want. We want to prove that for arbitrary epsilon there exists delta naught, let's say, greater than 0, such that for all x from, once again, I consider only right hand side version, right limit version, x tilde plus delta naught, we have inequality f of x over g of x greater than 1 over epsilon. That is what we want to prove for infinite limit. Okay, let's have a break. Перерывчик. Okay. So let's continue. So that is what we want to prove. And we know that the limit of ratio of derivatives, that one, is infinity. L is infinity. So it means what we know is that one. There exists delta, let's say delta 1 greater than 0, such that for all x from x tilde up to x tilde plus delta 1, we have f prime of x over g prime of x greater than 1 over epsilon, let's say. So maybe maybe 2 over epsilon. 2 over epsilon. So we know the limit of the ratio is infinity, and it means that this ratio can be made as large as we want for sufficiently close to x tilde, for x sufficiently close to x tilde. Okay, then once again we'll use the same expression, not the same. Now L is infinity, right? So quite analogous chain of representations. So f of x over g of x equals to f of x minus f of alpha over g of x minus g of alpha times 1 over h alpha of x. And now alpha should be taken where? Okay, alpha should be taken somewhere. Alpha is from x tilde up to x tilde plus minimum of delta 1. So both should be satisfied. G prime not 0 and the ratio greater than 2 over epsilon. Okay, so once again we can use the Coshi mean value theorem for such fixed alpha and for the segment x alpha, where x is between x tilde and alpha, and it gives us f prime of c over g prime of c times 1 over h alpha of x. That is greater than 2 over epsilon times, now it's clear what we should use about the function h alpha. So we know, as before, that the limit of h alpha of x equals to 1. It means there exists delta 3 greater than 0, such that for all x from x tilde up to x tilde plus delta 3. Now, I'll use, in fact, here for me it's enough to put just 1/2. 1/2 now. So we put here just 1/2. It's enough. Why? Because what follows from that inequality? From that inequality follows 1 over h alpha of x is greater than 1/2. And that's sufficient for us. Because now, look, I put here times 1/2. Both are positive because here positive, so we can multiply those two inequalities. That one and this one. And that is 1 over epsilon, so precisely what we wanted. And what's about delta naught? What's about delta naught here? Delta naught can be taken as minimum of all deltas which appeared, right? So delta 1, delta 3. Okay, let it be delta 3 as it was, because now we have no delta 2. Doesn't matter. And that is again a positive number, right? So it means once again we obtained the desired inequality. F of x over g of x greater 1 over epsilon. Okay? It means the theorem is proved completely. So, example. Okay, where to write? Okay, so example. Find the following limit: x tends to 0, logarithm x squared over 1 plus 1 over cubic root of x squared. So we have here f of x logarithm x squared. It is differentiable everywhere on R without 0. G of x is 1 plus 1 over cubic root of x squared. Also differentiable on the same set. And moreover, g prime of x, which is x minus 2 over 3 prime, that is minus 2 over 3 cubic root of x power 5, and that is never 0 everywhere on the same set, on the domain of that function. So differentiability is checked. Next is that limits f of x and x tends to 0. Limit x tends to 0, g of x is infinity. It's clear, right? When x tends to 0, x squared tends to plus 0, and logarithm tends to minus infinity. Yeah, in fact, I'm sorry. Here we have slightly different. Okay. Roughly speaking, I should consider minus. Put here minus, then we have limits are equal to plus infinity, right? And then we have no problem with it. Okay. Now let's consider the limit as x tends to 0, f prime of x over g prime of x. So what is it? That is limit of minus logarithm x squared prime over 1 plus 1 over cubic root of x squared prime. So that is x tends to 0, okay, minus then derivative of logarithm 1 over x squared times derivative of x squared, and that is 2x. The derivative of denominator we computed before, minus 2 over 3 cubic root of x power 5. And okay, what it gives? It gives limit as x tends to 0, cubic root of x squared over 3. That's it. So here we have x power 5 over 3 in numerator, x power 1 in denominator, so x power 2 over 3 in numerator. And that is 0. That is 0. Hence, what we obtain? We obtain that by our theorem, limit as x tends to 0, f of x over g of x, and that is precisely minus limit as x tends to 0, logarithm x squared over 1 plus 1 over cubic root of x squared, and that is equals to 0. Equals to 0. Okay? So we have found the limit is 0. And there are two more versions in your lecture notes concerning limits at infinity. So both cases can be also extended to the case of limits at infinity, right? So let me write remark. L'Hopital rule, both cases are valid, is valid for limits at infinity as well. I'll not write down all details. They're written in your lecture notes, in fact, but I don't think it's a good idea. Yeah, so in fact, there is extra condition of finiteness, but you need not to suppose finiteness of the limit. It's not necessary. So two more examples. Example 2, let's say. Okay, let it be example 1. Example 2. limit as x tends to infinity 1 over x times pi over 2 minus arctan x. Maybe maybe a couple of words about proof of the remark. Okay, let's firstly solve the example. So, how to proceed here? Here we represent it as limit as x tends to infinity, plus infinity, right? 1 over x over pi over 2 minus arctan x. So, now you see f of x is 1 over x, g of x pi over 2 minus arctan x, and both tend to 0 as x tend to infinity. Okay, so what's about differentiability? F prime equals to minus 1 over x squared, differentiable everywhere except 0, so in the neighborhood of infinity at least it is valid. It is differentiable. G prime of x is minus 1 over 1 plus x squared, so it exists everywhere, hence g is differentiable everywhere. And according to L'Hopital rule, we can proceed like 1 over x prime over pi over 2 minus arctan x prime, that is limit x tends to infinity minus 1 over x squared over minus 1 over 1 plus x squared, that is 1 plus x squared over x squared, and we can rewrite it as 1 over x squared plus 1. This tends to 0, so the limit is equal to 1. And couple of words about proof of the remark. So, proof for remark. So, we want to consider, let's say, x tends to plus infinity f of x over g of x. And we can substitute x equals to 1 over t. Then it means that we are interested in the limit t tends to 0 plus f of 1 over t. 1 over t. Now we can use L'Hopital rule. Why? Just we'll see it later after differentiation. So let's differentiate according to the chain rule. Limit t tends to 0 plus f prime at 1 over t times minus 1 over t squared over g prime 1 over t times minus 1 over t squared. Then we cancel those extra terms minus 1 over t squared. So what remains is just f prime 1 over t over g prime 1 over t, and that is limit as x tends to infinity f prime of x over g prime of x. That is how it works. Again, somebody's joking. Okay. So, that's it. Now, one more example. Example 3. Yeah. 3. The limit as x tends to infinity logarithm x over x. Once again, we have here put f of x equals to minus logarithm x. Oh, wait, no. It's okay, here it's okay. Don't need to put minus here. So f of x is logarithm x. It's differentiable. And the limit as x tends to infinity, f of x is infinity, plus infinity. Then g of x is x, and the limit as x tends to infinity, g of x is also infinite. So we can proceed by L'Hopital rule as logarithm x prime over x prime, and that is limit x tends to infinity 1 over x over 1, and that is 0. And this is how it works. I would like to consider one more example, which will be useful in the next section. Okay. Example 4. Consider the following function. F of x equals to e to the power minus 1 over x squared if x not equals to 0, and 0 if x equals to 0. We'll prove that all derivatives at 0 exist and are equal to 0. That is, of course, yeah, definitely we may apply L'Hopital rule many times, and in fact, just now, that is an example when we'll apply it infinitely many times. I mean, no, I'm wrong. Not infinitely many. Finitely many times, but as much as we want. Yeah. Okay, so let's start with proof. In fact, we'll use the following idea. Let's compute first derivative, f prime of x for x not equals to 0. It is clear it will be just the exponent itself times derivative of minus 1 over x squared, and that is minus 2, so e to the power minus 1 over x squared times 2 over x cubed. Okay, then look, what is about f prime at 0? Let's compute it by definition. That is limit as x tends to 0, f of x minus f of 0 over x minus 0. F of 0 is 0 by the definition, so we have limit as x tends to 0, e power minus 1 over x squared over x. And it's easier to replace x by 1 over t. Then we'll rewrite it as limit as t tends to, okay, in fact it doesn't matter, let me compute firstly, t tends to plus or minus infinity. Let's write it like that. So we'll compute both limits as t tends to plus infinity and minus infinity, and they're equal, we'll see it. E power minus t squared over 1 over t, and we'll replace it. So we have two limits, t tends to plus infinity and minus infinity, and t over e to the power t squared. And by L'Hopital rule, we can write it as t tends to plus or minus infinity, 1 over 2t times e to the power t squared. Now you see that we have infinity in denominator, so that is 0. That is 0. So n equals to 1 is checked. Now what to do for next? For example, for second derivative, once we computed the first derivative, we can compute analogously the second derivative. So second derivative is 0 at 0 is limit as x tends to 0, f prime of x minus f prime at 0 over x minus 0. Now we know f prime at 0 is 0, so we can proceed in analogous way. E to the power minus 1 over x squared times 2 over x cubed over x. That is limit as t tends to plus or minus infinity. Once again, e to the power minus t squared 2t cubed 1 over t. That is limit t tends to plus or minus infinity 2t power 4 over e power t squared. And now we have precisely the situation of the question. So look, we apply L'Hopital rule once. We have 8t cubed over 2t e to the power t squared. So cancel 1 power of t, and okay, let me rewrite it as this one, t squared over e to the power t squared. So once again, we apply L'Hopital rule. It gives 4 times the limit t tends to plus or minus infinity 2t over e to the power t squared times 2t. Now cancel those 2t, and we have 0. So, but how this application of L'Hopital rules several times works? Look, we differentiate both numerator and denominator, but we don't know if the limit exists at the moment. So what we do? We transform a little bit and then apply L'Hopital rule once again. Now it's clear it exists, hence by L'Hopital rule once we have this limit also 0, and then L'Hopital rule twice, we come back to our limit. So that is how it works several times. Okay, that is for second derivative. But now what to do further? We need to prove for arbitrary n. But look, what is f second derivative at arbitrary point x not equals to 0? So what we have here? E to the power minus 1 over x squared times 2 over x cubed prime. Derivative of exponent we know, that is 2 over x cubed, it will be in square, because we multiply twice. And then minus, if we differentiate second, we have 6 e to the power minus 1 over x squared times 1 over x power 4. Okay, so how we can try to understand what is it in general? So let me write it down like that. E to the power minus 1 over x squared times what we have here. We have here the following thing. So minus 2 over x, 4 over x power 6 minus 6 over x power 4. Okay, what is it? That is a polynomial. A polynomial. Let me write it. That is a polynomial. So e to the power minus 1 over x squared times a polynomial of 6th degree 1 over x, where p6 of t equals to 4t minus 4t power 6 minus 6t power 4. And this expression suggests the general idea. So let's prove. So prove that f nth of x equals to e to the power minus 1 over x squared times p, it was 3n of 1 over x, where p 3n of t is a polynomial of degree 3n with leading coefficient 2 to the power, which power? 2 to the power n. 2 to the power n. Maybe minus some APs? No. Here we have, I made a mistake here. Here I have minus, yeah. So it's minus, here minus, yeah, so minus 1 power n. That's it. Yeah, that is leading coefficient. Okay, prove the following thing. By induction, we we checked n equals to 1, n equals 2. We checked. Here, of course, I should suppose x not equals to 0, right? X not equals to 0. N equals 1, n equals to 2, we checked. You see, n equals to 1. Minus 1 power n plus 1. Yeah. 2, n equals to 1. 2 to the power n. Yeah, it's okay. Yeah, so, and if we have checked for n equals to m, induction hypothesis is okay, then what is about f m plus 1 of x? That is the derivative of such an expression. And what is it? That is e to the power minus 1 over x squared times minus 2 over x cubed times p 3m 1 over x plus p 3m prime of 1 over x times minus 1 over x squared. So that is precisely times p 3m plus 1 of 1 over x, where p 3m plus 1 is a polynomial of degree, 3 times m plus 1 of degree 3m plus 3. Why? Because here we have polynomial of degree 3m times 1 over x cubed gives a polynomial of degree 3m plus 3. And here we have polynomial of degree 3m minus 1 plus 2 gives 3m plus 1. Altogether 3m plus 3. Leading coefficient we multiply by minus 2. That coefficient is preserved. Okay, so we have proved that by induction, and the last step, now we are able to prove the desired result. So nth derivative at 0, limit as x tends to 0, derivative of the order n minus 1 at x minus n minus 1 at 0 over x minus 0. Once again, we prove it by induction. So we suppose this is 0. And then we proceed as we did for the second derivative. So look what we have here. E to the power minus 1 over x squared times polynomial p3n of 1 over x over x. So we replace 1 over x by t, and analogously by this, applying several times L'Hopital rule, it's clear that it will be 0. And that's all for today. Then. Okay, thank you.